any kind of elongation, there is no any kind of indication at the point of fracture, we can easily see, right. Now below that particular figure we can see a line diagram of ductile material and brittle material. See, a external force is applied downward to the ductile material, right, and it is goes under bent position, right. So ductile material shows indication and it is now bent, whereas brittle material cannot be bent and suddenly it goes under fracture. So this is the difference between ductility and brittle. Now the another property is malleability. It is a special case of ductility where it can be rolled into thin sheets. Now observe carefully this particular figure which is shown below. Dear students, material which has a ductility and all the ductile material cannot be rolled into thin sheets, right. Every material which can be rolled into thin sheets is a ductile material, but every ductile material cannot be rolled into thin sheets. We should keep in mind that particular point, right. Now if ductile material can be rolled into thin sheets, then we can say that that particular ductile material also possesses the property of malleability. So malleability is nothing but it is a special case of ductility where it can be rolled into thin sheets. Generally we use in our home appliances and different engineering applications are there in which we use a thin sheets of metal, right. So whenever the material can be rolled into thin sheets, that particular property is called malleability. Now dear students, we will understand resilience. This is the property of the material that enables it to resist shock and impact by storing energy. The measure of resilience is the strain energy absorbed per unit volume. In other words, we can say that whenever material or whenever the object can resist shock and absorb the energy, or we can say it can store energy, we can say the particular material has a good resilience power. Again, this is just a property of material that enables it to resist shock and impact by storing energy. The measure of resilience is the strain energy absorbed per unit volume. So we can measure a resilience of particular material by measuring it in a energy, or we can say strain energy absorbed per unit volume, right. Now dear students, we will switch over to toughness. This is the property which enables a material to be twisted, bent or stretched under impact load or high stress before rupture. It may be considered to be the ability of the material to be absorb energy in plastic zone. The measure of toughness is the amount of energy absorbed after being stressed up to the yield point of fracture, right. So we can say in other words that material, if it enables us to bend it, stretch it, or we can twist that particular material without any fracture, and if that particular material withstands twisting, bending and stretching, then we can say that particular material is tough, right. And it may be considered to be the ability of the material to absorb energy in the plastic zone. Also we can say that if material can absorb energy in its plastic zone, then also it is a tough material, right. The measure of toughness is the amount of energy absorbed after being stressed up to the point of fracture, that we can understand easily. Now dear students, we will try to understand the phenomena of creep. It is defined as the time dependent and permanent deformation of materials when subjected to a constant load or stress. Creep is normally an undesirable phenomenon and is often the limiting factor in the lifetime of a part, right. Earlier whatever the properties we seen, few of them are the desirable properties, but creep is one of the undesirable property which limit the lifespan of any particular part, right. Now basically creep is defined as the permanent, if there is a permanent deformation of material when subjected to a constant load or stress. Now we can see there are several machine parts, for example bush, for example visor. These all are the materials which generally always subjected to a constant load or stress, right. So after some particular time is passed, we will see some amount of fracture, some amount of deformation in that particular object, right. So this is the creep phenomena, in which we can see deformation due to time period and deformation due to static load. Mind well students, there is no variation in load, there are no any cyclic load applied, or particular object is not subjected to a variable load. Only static load is applied, and if it is a time dependent, then and then creep phenomena can be seen, right. So these are the properties which we studied today is static strength, resilience, fatigue strength, toughness, plasticity, malleability, creep, elasticity, ductility and brittleness. These all are the properties are mechanical properties, and they are very important to be understood before knowing the basic types and various categories of different engineering materials. Okay, dear students, I hope you have understood these different properties very well. Now we are going to categorize different materials, right. So here we can see classification of engineering materials. The engineering materials are classified into three groups. First category is it is metal and their alloys. Second category is non-metal, and third category is composites. So generally any material we can differentiate it in a metal, non-metal and composites. Alloys are also there, right, and definition and the basic phenomena of the alloys we will see later on, right. But here we will just keep in mind that three types of materials are there: metals, non-metals and composites. Okay, now the metals and their alloys are further classified into two groups. First it is ferrous alloys, and second it is non-ferrous metals. So there can be a ferrous metal, non-ferrous metal, and also there can be a ferrous alloys and non-ferrous alloys, right, and that is the further classification of two groups. Now let us understand that metals are divided into two types, that is, and first is ferrous metal. What is a ferrous metal? Ferrous metals are those which have iron, or it is a symbol of element is Fe. So ferrous metal are those which have iron as their main constituent, and are made by refining pig iron and adding other elements to improve mechanical properties, right. So whenever there is Fe, iron is present in a major portion, in a major amount, then and then that metal is called ferrous metals. There can be some other impurities or other element added, but there is some physical performance part. They have to perform some basic, fulfill some proper characteristic. That's why we can add that particular other elements. Otherwise, in every ferrous metals, the ferrous, or we can say iron, works as a main constituent. There are a few examples are given: cast iron, wrought iron and steel. These are the basic example of ferrous metals. Now we will see non-ferrous metals. Light metal groups such as aluminium and its alloy, magnesium, manganese alloys, copper based alloys such as brass, bronze, white metal group such as nickel, silver, white bearing metals, right. These all are the example of non-ferrous metals and non-ferrous alloy, right. In non-ferrous metal and in non-ferrous alloys, there will be no any form of iron will be present, right. There will be no iron Fe will be present over there. Now ferrous alloy materials. Cast iron, it is an alloy of iron, carbon and silicon and manganese. Now we are going to understand what is cast iron, and it is said that an alloy of iron, carbon and silicon. Carbon content may be within 1.7% to 3%, and carbon may be present as free carbon or iron carbide, right. So if carbon is present in form of pure carbon or in form of carbide, that is iron carbide, that is Fe3C, right, and the main constituent is iron. So in a cast iron there is a proper mixture of iron and carbon, then it is a cast iron. In general, the types of cast iron are grey cast iron, white cast iron, malleable cast iron, sphered or nodular cast iron, austenitic cast iron and abrasion resistant cast iron. These are the different types of cast iron, right. Now advantages we will study of cast iron is, cast iron we can cast it into intricate shape, right. So generally whenever we do forging and casting, it is made up of cast iron. Then we can make complex part and complex shape also can be generated from the casting. Another advantage of cast iron is it has a high compressive strength, good wear resistance, excellent machinability, right. Whatever the object or machine part which is made up of cast iron can have a high compressive strength and can be compressed up to very high extent. It also has a good wear resistance. Any component or any machine part which is made up of cast iron can resist wear and tear, and then it has an excellent machinability, right. So if any component or machine part which is made up of cast iron, we can easily do any kind of mechanical and machine operation, right. So that is the very vital and important property of cast iron, that it possesses a excellent machinability. Now there is a limitation of cast iron also, that is poor tensile strength, right. The cast iron component shows a poor tensile strength, it has a poor tensile strength. Now we will see applications, that is machine tool beds, column guideways, bearing housing, pulley, flywheel, couplings, brake drum and clutch plate, right. These are the practical applications in which all the components and all these are objects made up of cast iron, right. So these are the basic application of cast iron. Now we will understand grey cast iron. Carbon here is mainly in the form of graphite. As we already studied that in a cast iron the main constituent is iron and second main constituent is carbon, right. Iron and carbon are two major constituent of cast iron. But here in a grey cast iron, carbon always present in a form of graphite, and this type of cast iron is inexpensive and has a high compressive strength. Graphite is an excellent solid lubricant and it makes it easily machinable but brittle, right. So whenever there is a grey cast iron and a carbon is present in form of graphite, right, that particular object will have high machinability and will possess a property of brittleness. So particularly grey cast iron has a high brittleness. Also it has a excellent solid lubricant properties, right. So this is also another important property of grey cast iron. Now some example of this type of cast iron given, that is FG20, FG35, FG150, FG200, FG260 and FG300, right. Here F and G shows nothing but F stands for Fe, that is iron, and G stands for graphite, and 20, 35, 150, this number indicates ultimate tensile strength in megapascal, right. These are the designation of grey cast iron. Now another type of cast iron is alloy cast iron. Cast iron is alloyed with alloying elements like nickel, chromium, molybdenum, vanadium and silicon to form the cast iron. This iron is used to improve the properties of cast iron. Now see, it is not that all the properties or all the characteristics which are desired for any engineer will be there in cast iron, right. So we have to also add some extra elements in that particular mixture of iron and carbon, right, because cast iron have only two major constituent, it is iron and carbon, but now we have to add some extra elements, and that is a nickel, chromium, vanadium, molybdenum, silicon, right. Now we will try to know that what are the basic reason, what are the main reason behind adding this particular elements, this particular extra elements, right. But we will keep in mind that in all alloy cast irons there are some extra elements added in a considerable amount. Now alloying elements in alloy cast iron, why we add nickel? The portion of nickel added up to 5%, and we add nickel to increase the strength and wear resistance. Then we add chromium in alloy cast iron, we add chromium up to 3%, and because as we have added chromium, the property of hardness and wear resistance will be increased in particular object. Now we can add molybdenum in cast iron up to the 1.25%, and that will increase the hardness and also tensile strength of cast iron. There is vanadium also. We can add vanadium in cast iron up to the 0.5%, and that vanadium will increase tensile strength of particular material. Also silicon is there. We can add it up to 2.5%, and that will increase stability. So dear students, we can easily see here that different reason behind adding different materials, different elements in cast iron is nothing but to improve or to expand some of the properties of cast iron, right? So by adding extra elements, we can improve or we can add some of desirable characteristic and some of desirable properties in cast iron. Okay, now let us understand plain carbon steel. It is alloy of iron and carbon. Less than 1.7% carbon is present over here, with small amount of manganese in less than 1.5%, silicon less than 0.5%, sulfur and phosphorus. So plain carbon steel is a mixture of iron, carbon, and extra element which is added is manganese, silicon, sulfur and phosphorus, right? Now let us see the types of plain carbon steel. Dead mild steel up to the 0.15% carbon if added. In a low carbon steel, or we can say mild steel, there is a less than 0.3% carbon is added. In a medium carbon steel, there is 0.3 to 0.6% of carbon is added, and in high carbon steel there is 0.8 to 1.5% of carbon is added, right? So this is the basic phenomena of plain carbon steel. Now there are few advantages of using plain carbon steel. It always shows high strength, ductility, high impact loading, and high resilience and toughness. This is the basic property, and we can say advantageous property of plain carbon steel. Limitation of plain carbon steel is poor wear resistance, and it cannot cast intricate shape, right? So plain carbon steel cannot be casted into intricate shape. So we cannot generate, we cannot made complex shapes from plain carbon steels. Now there are a few applications of plain carbon steel. It is automobile body, spindles, levers, light duty gears,